So we had obtained this, if you remember, the Planck's law of black body radiation in terms of frequency, and to derive this we had used Bose statistics, the Bose Einstein distribution law, which is this. And just for your recapitulation, we are uh, talking about a system where the constituent particles are bosons, which means that they can occupy, any number of the particles can occupy a given state, and Ni by Gi, that is the occupation index, is much greater than 1, sorry, of the order of 1, so that we have to follow quantum statistics. Okay, and this is the distribution law. Now so what we want to discuss today is, we talk about the Bose Einstein distribution function under limiting conditions. Okay, what are the limiting conditions? See, this is the function. This is the Bose Einstein distribution function, 1 by e to the power alpha, e to the power beta, ei minus 1, where ei is the energy of the ith cell, and beta and alpha are the Lagrange's undetermined multipliers. Okay. Now we have to remember that since E is the energy of a given state, but if we have not spoken of thermodynamical considerations related to this statistics till now. Okay, that again is a portion that was supposed to be done by BSR. But having said that, we have to remember that dE is equal to TdS. This we all know, right? And since the entropy S is has this expression, Boltzmann constant multiplied by log of this W, the work function, the thermodynamic work function. So if you write ds in place of ds, if you write this k d of ln omega, or rather W, as we have used the notation here. So using the expression of W from what we have derived in our earlier class, we can see that d takes this form. Okay, so if you differentiate this expression inside the summation over here, then if you follow, I have not spent time in this class doing that derivation, but if you follow the procedure same as you have done in Maxwell-Boltzmann statistics to obtain the form of beta, then using exactly that procedure, if you take the derivative of this expression here, considering that Ni is the variable parameter and Gi is a constant, then it can be shown that the Lagrange's multiplier beta is equal to 1 by kt, where k is Boltzmann constant. Okay? Some books use small k, some books use capital K. So it's just, you have to just mention that k is Boltzmann constant. Okay, so that we know that the Bose Einstein distribution function is of the form 1 by e to the power alpha e to the power ei by kt minus 1. Now, if the temperature is very high, if we raise the temperature of the system to extremely high values, then obviously temperature is the total energy is basically related to temperature. We know that the temperature is the manifestation of the total internal energy of the system. So if the temperature is raised to a very high value, we have to keep in mind that the energies also have a very wide range. So the particles will then have a very wide range of energies. Okay, which means that we have reached a rarefied condition, right? Because more the number of energy levels available, that is more the range of energy available to a given number of particles, more is its scope of choice, right? Again, if we go to the job and aspirant scenario, If you have more jobs at hand, you have more choice to choose. But if the number of jobs and the number of applicants become almost same, then there remains no choice. So basically, when we are raising the temperature of the system, we are providing a particular particle with a larger range of energies, which means that since the number of particles does not change, and yet I have changed the temperature of the system, I've increased the temperature of the system. So this means that we are talking about a rarefied condition. Lesser number of applicants, more number of jobs. Okay. So what happens? This means that GI is much greater than NI. Okay. And we know that this is typically the condition of classical, what should I say? Classical treatment, let's say. Okay. When GI is much greater than NI. Okay. So in this expression, we have derived this expression before while coming to the final expression of the distribution function. So here in this expression, where we had introduced the Lagrange's multipliers alpha and beta, ln ni plus gi by ni minus alpha minus beta equal to 0, since gi is much greater than ni, this expression boils down to ln gi minus ln ni minus alpha minus beta a equal to 0. Now you must have recognized this as the Maxwell-Boltzmann distribution. This, if you take it to the exponential form, what you will get is the Maxwell-Boltzmann distribution function, where the difference is in the denominator. Here it is 1 by e to the power alpha e to the power beta ai minus 1. Here it becomes just 1 by e to the power alpha e to the power beta ei. Okay. So this minus 1 is not there. That is the difference between the MB distribution function and the B distribution function. The introduction of B postulates results in the condition where the arrangement of the particles in the available cells is done in such a way that the manifestation in the final expression of the distribution function is only the fact that the denominator does not contain the minus 1 in MB, and it does contain the minus 1 in the B distribution function. Okay. So what we can see is that under the limiting condition of very high temperatures, Bose Einstein statistics boils down to Maxwell-Boltzmann statistics. So when the temperature is very high, the system behaves classically, and Maxwell-Boltzmann statistics is sufficient to describe it, and we do not have to cater to quantum statistics under these conditions. Okay. So this is the condition of high temperature, and you just have to keep in mind that at high temperature, Bose Einstein distribution formula boils down to Maxwell-Boltzmann distribution formula. Okay. And if you have done this derivation, then it's well and good. If you have not done this derivation, that is how to get the expression of beta from this relation d equal to t ds equal to tk d of ln w, then please inform me in WhatsApp and I will send you the derivation. All right. Okay. Now that we have done the high temperature part, what happens when the system is taken to very high temperatures? Let us see what happens when the system is taken to very low temperature. Now, when the system is taken to very low temperature, that is when something novel happens. Okay, and that is what is popularly known as Bose Einstein condensation. All right. So you know, when the temperature of a system is lowered, then what we get is condensate. When the temperature of water vapor is lower, it condenses to liquid water. Okay, so on similar lines, we call this phenomena condensation when the temperature is lower. Okay, now in a nutshell, what is Bose-Einstein condensation? In very naive language, is that it is a quantum phenomena in Bose gases, that is for particles which follow Bose statistics, that is bosons, where a large number of bosons simultaneously occupy the ground state of the system. Okay, what happens here? When you have a Bose system containing bosons, when the temperature is lowered, it is observed that the ground state has a lot of crowding. It seems that all the particles have a tendency to go and sit in the ground state as the temperature is lower. Okay, so several bosons simultaneously occupy the ground state, and that exactly is called what is popularly known as Bose-Einstein condensation. This was predicted in as early as 1924 and 1925 by Einstein. Remember, Shoten Bose, his paper was precisely on the fact that he visualized EM radiation as a photon gas. Okay, he visualized EM radiation um, as something which can be thought of as a gas, where the gas particles are photons with energy hν. And using this idea, he derived Planck's radiation law, and his idea, the idea which he used, treating the light particles, the photons, as gas particles, calling it a photon gas, he actually could get back to Planck's radiation formula. Okay, so that paper he had sent to Albert Einstein. Einstein further generalized it. Okay, Einstein saw that yes, this was correct, and he further generalized the whole thing, and together they gave us what is known as the Bose-Einstein system, and they predicted that since bosons are particles which do not obey Pauli's exclusion principle, therefore as you lower the energy of the system, as you lower the temperature of the system, the crowding of the ground state is a possibility. Okay, so the prediction was done as early as 1925. However, to observe Bose-Einstein condensation experimentally, it took another 70 long years. 70 years, okay, it took experimentalists to actually reproduce Bose-Einstein condensation in the laboratory. Okay, observed in 1995 by these three chaps, Wyman, Cornell and Kettle, and actually this was sort of happening in, I think, in two labs simultaneously in US. They were actually, in fact, this experiment was being done for, since its prediction in 1925, the study was on to experimentally observe it. So just a second. Okay, and there were these two groups actually, who sort of almost simultaneously observed this phenomena, but just we have to remember that it was a long gap of 70 years, and finally it was observed first in 1995 at MIT, Massachusetts Institute of Technology, using a magnetic trap. You can go to the internet, Google Bose Einstein condensation, and there is this paper in Physics World which is produced from MIT. And this is a paper of 1997. If you go through the paper, they have described beautifully the experiment that was done, uh, in which they observed this condensation. Okay. Um, So I will not describe the experiment, just the fact that it was finally observed, and so it was, the prediction was proven, and this fetched them the Nobel Prize, of course. And I don't know how many of you saw the YouTube video that I sent you in the group, showing how many Indian scientists were denied the Nobel Prize despite the fact that they made some breathtaking, path-breaking postulates, discoveries, etc. So the particles were, what should I say, theoretically given by Bose, the theory given by Bose with Einstein, uh, but he did not get the Nobel Prize. But based on his work, several other people got the Nobel Prize in the coming years. Okay, half the particles in the universe follow statistics are after the name of a person who did not get the prize. Anyway, so now what happens is, see, at room temperature, so I will try to qualitatively tell you what Bose-Einstein condensation is, and just describe a little bit of that paper that I mentioned, and I've already sent you the paper for you to go through. So at room temperature, the matter waves, if you consider the matter waves attached to individual atoms, they are uncorrelated, okay, they are disordered. And so we can easily describe the gas using Boltzmann statistics. As I told you, that when the temperature is high, then the GI is greater than, much greater than Ni, and we can easily use Boltzmann statistics. However, GI is greater than Ni. However, when the gas is cooled, the number of atoms in each cell has dimension h cube, as we discussed extensively in one of our classes. So the number of atoms in each cell of dimension h cube becomes more than 1. Okay, and therefore the wave functions related to adjacent atoms, they overlap. Each atom has its own wave function, and since they are so close together, occupying sometimes the same cell simultaneously, their wave functions overlap, and therefore the atoms lose their identity. Okay, and therefore we now have to use quantum statistics to see what rule is governing the behavior of the gases, that's particles. Okay, so Bose-Einstein statistics dramatically increase the chances of finding more than one atom in the same state, precisely because Pauli's exclusion principle is not obeyed by boson. Now, when you lower the temperature and GI becomes almost equal to Ni, you can also apply Fermi-Dirac statistics. But the constraint in Fermi-Dirac statistics is that there is the restriction of occupation. FD statistics says that only one particle can occupy one chamber. So particles following FD statistics will follow a distribution law in which that has to be incorporated. So we cannot have crowding of cells. That is not allowed in FD statistics. But Bose particles, they do not follow Pauli's exclusion principle, and there is no restriction on crowding of cells. So in order to attain the lowest energy states, they would often go and crowd in a cell that has the lowest energy. Okay, it's like, you know, people would, even if a place is very cramped, but people who do not have sufficient, say, money, they will go to that cramped place because they would have to pay less rent. All right, you understand what I'm trying to say? So even if there is lesser place, but if the owner of that apartment, say, has no restriction on the number of people staying in that apartment, then people who cannot pay high rent, who don't have enough money, they will agree to stay in that cramped place with other people just because they have to pay less rent. So similarly here, in order to attain the lowest energy state, the particles will agree to share the cell with several other particles simply because there is no restriction on the occupation number. Okay, and therefore there is this crowding that takes place, but only in case of Bose particles, not for Fermi particles, because there the restriction of Pauli's exclusion principle is imposed. Okay, now as the temperature goes to 0, we obviously have to have alpha tends to 0. This is clear from the expression. Okay, so why do we have to take alpha equal to 0 as the temperature goes to 0? Let us look at this expression. Okay, let us look at this expression. This e to the power alpha e to the power e by kt minus 1. So t tends to 0 means this term goes to infinity. So obviously, in order that this remains finite, alpha must be 0, right? It is only then that this will give this term will remain finite. So as t is decreased, alpha must go to 0, and therefore the distribution function becomes this 1 by e to the power ei by kt minus 1. Okay, and therefore at absolute 0, the particle will tend to occupy the lowest available energy state. Once again, in order that this remains finite, ei, uh, the lowest available ei would be sought by most of the particles, and they will go and crowd in that state which has lowest energy. Okay, and that results in what is known as Bose Einstein condensation. Okay, so I'll just look at that paper once with you, the initial part. Okay, so see, I have highlighted some portions. See, can you see this paper, everyone? This paper is by, this is basically a lecture by Matthew Schwartz. I have forgotten the university. Okay, these are open source materials, and you should all avail these materials since they so readily available. In fact, I have looked up Patria, I have looked up Raif, I have looked up Huang. I have not found any book where something suitable to your course is there, following the line of topics that is given in your syllabus. There is one book that based on the CBCS syllabus that has been brought out by Upendranath Nondi of Scottish Church recently. I have not gone through the book. Maybe he has something in this written in this similar fashion over there. I don't have the book, so I couldn't refer to it. Okay, so basically what he says is that there is no quantum effect preventing the particles to be in the same ground state, and naturally particles want to be in the state of lowest energy. Okay, so he asks, how many bosons do you expect in the ground state? Okay, now suppose that they obey Maxwell-Boltzmann statistics, so that Ni is of the order of this, e to the power minus ei by kBt. Now this function is pretty flat when the energy is much less than kT, Boltzmann constant into temperature. Okay, so if you take suppose 100 states below the value of kT, then you don't change the number of particles, you just take 100 states that are available for the particles to occupy. Then each one should be roughly having the same number of particles in it. Okay, So there is nothing special about the ground state if you are following Maxwell-Boltzmann statistics, because more or less half the particles will be distributed above and below. Okay. However, if you take, so what he has done is he has just talked about a two-state system. When you have a two-state system, you can talk about a canonical ensemble. But if you go to a number, if the number of systems become very high, the number of states become very high, then you cannot any longer talk about a canonical ensemble. You have to talk about a grand canonical ensemble. If you take a canonical ensemble with just two energy states equal to 0 and equal to E, then if we apply both Maxwell-Boltzmann and Bose Einstein statistics, then we'll see that in this two-state system, the ground state occupancy is much larger than n by 2, even with KBT much greater than the energy, if you use Bose Einstein statistics, okay, but not with MB statistics. That does not give you anything novel about the ground state. So what he has done is he has calculated the partition function, okay, for the two-state system, and it is very easy to calculate because one state has energy 0 and the other state has energy epsilon. So the partition function, which is the sum of the two, which is just 1 for the 0 and e to the power minus beta epsilon for the one with energy epsilon, okay. And then he has found the probability of finding the particle in the ground state, which is e to the power minus beta epsilon naught by z1. So for the ground state, it will be 1 by z1, and the expected fraction of particles would be this 1 by 1 plus e to the power minus beta e. Okay. So this is for only one particle. So for Maxwell-Boltzmann, I won't go through this mathematics. I'll just show you the graph that he has done. This is actually a computer simulated graph that he has done numerically for n equal to 100, okay, n equal to 100 particles and two states. 100 particles trying to occupy two states, okay. So what is seen is that you can see that the Bose Einstein curve is this, the blue one, whereas the Maxwell-Boltzmann curve is the brown one. You can see that the Maxwell-Boltzmann curve is flatter, much flatter, okay. So this plot basically demonstrates Bose-Einstein condensation, all right, for a very small system, but nevertheless it is demonstrated. See, as the temperature is lowered, the particles start coming to the ground state. From here, the phenomenon begins. Whereas for Maxwell-Boltzmann, you have to go right to absolute zero in order for this variable to shoot up. Whereas in Bose-Einstein, it starts shooting up gradually from a considerably higher temperature as the temperature is lowered. Okay. Yes, see, with Bose-Einstein statistics, a significant fraction of the particles are in the ground state, even well above the temperature which gives KBT equal to E. Okay. So once again, as I told you in the beginning, that this is just a qualitative discussion that I have done in this class. So this is another curve showing the approximation to the Bose Einstein curve, n ground by n, the fraction of particles in the ground state by the total number of particles plotted against KBT by n, total energy. Okay. So as I told you in my WhatsApp message also, you can go through this paper and see what it exactly says. This is just for further reading, as I told you. And since I got to know about this portion that was left, it had gone totally out of my mind that I was left to do this portion. So I have not been able to speak to anybody regarding this. I have prepared this only yesterday. So I'll speak to my the teacher who I know in the board of studies, and I'll ask him whether numerical uh, anything numerical should be done in order to understand Bose Einstein condensation, or whether the qualitative discussion is enough, and if it is required, then I'll provide you with it. Okay. So just in a nutshell, just remember that Bose Einstein condensation is a phenomena where, since bosons have no restriction on multiple occupancy of a single cell, so when the temperature is lowered, particles seek the lowest energy state, and there being no restriction, they tend to occupy the lowest available energy state, and therefore there is a crowding that takes place, and that is exactly what is known as Bose Einstein condensation. Okay. Now the last thing that we are supposed to do in this portion of the syllabus is the case of liquid helium. Okay. Now, liquid helium is again explainable both through FD statistics and BE statistics. We will do the BE portion. This is one of the most remarkable elements in nature, liquid helium. Okay, it has very several novel properties, and makes it an element which is extensively studied because of the exclusive and peculiar properties that it shows. The most peculiar property being that it is the only substance that remains liquid under ordinary pressure at absolute zero. All the other elements, they freeze when taken to absolute zero. Liquid helium is the only element that remains liquid at ordinary pressure. We have to remember, in order to state the in order to specify the state of our system, we have to specify both temperature and pressure. So under ordinary pressure at absolute zero, helium remains a liquid. The solidification of helium will take place only when external pressure exceeds almost about 25 atmospheres. Okay. So until that condition, it remains liquid, which is a very rare phenomena. In fact, it is the rarest phenomena. Now, if you consider classical physics, then the prediction of classical physics is that at absolute zero, all movement ceases. We have all learned this from our the beginning of when absolute zero of temperature was introduced to us. It is called absolute zero because the particles, the movement of the particles cease at this temperature, right? So that is what we have studied classically. So the fact that helium does not freeze, it remains liquid even at absolute zero, that entices some novel quantum mechanical explanation. It cannot be explained through classical mechanics, and it can be explained only using quantum mechanics. Okay. Now, helium atoms, there are two kinds of helium atoms available in nature, helium-3 and helium-4. Okay. Now, helium-3 atoms have nuclear spin half, whereas helium-4 atoms have nuclear spin 0. So, the ones with nuclear spin half would follow FD statistics, whereas the ones with nuclear spin 0, they will follow BE statistics. So, the same element, but the different varieties that are available in nature follow two different kinds of statistics. Otherwise, they are virtually same. They are identical chemically. They have no difference in their chemical behavior. But their nuclear structure gives them slightly different masses, and the fact that one has spin half makes them fermions, whereas the other fact that they have spin 0 make them bosons. So helium atoms can be either fermions or bosons. All right. So He4, being a boson, exhibits second order transition to a superfluid state. Now don't ask me what this is all about. You have not done critical phenomena. You know, however, from thermodynamics what is second order phase transition. Okay. So basically Bosons are particles which undergo second order phase transition and they transit to a superfluid state. Okay. How is this observed? This is observed through an abrupt jump in the liquid specific heat. If you have done in thermodynamics, which again I was supposed to do and we did not get enough time to finish thermodynamics, if I remember properly, we were still in normal college days at that time. So in second order phase transition, the specific heat makes a discontinuous jump. Okay, so that discontinuous jump was observed in helium 4 system, and this is the graph showing that discontinuity. Okay, so temperature in Kelvin is increased and this is the specific heat capacity, and you can see that at a certain temperature 2.17, sometimes 2.19 Kelvin, there is this discontinuity in the specific heat. Okay, this abrupt change, this abrupt jump shows us that it undergoes a second order phase transition. Now at low temperatures, helium has 4 phases: solid phase, liquid phase and vapor phase, but there is more than one liquid phase. There are 2 liquid phases, one solid phase and one vapor phase, but 2 liquid phases. Okay, so the specific heat temperature graph, if you have observed, it resembles the letter lambda. Okay, if you see this, the specific heat temperature graph, this resembles the letter lambda, so that abrupt change is called the lambda point. It's a very popular subject of study among people who research this phenomena, and it's called the lambda point. Okay, now above this temperature 2.19 or 2.17 K, it is called helium 4 is called helium 1. It shows normal liquid behavior, normal fluid behavior, but below 2.19 K it is called helium 2. This 1 and 2 are not related to the atomic numbers. Okay, these are just phases: helium phase 1 and helium phase 2, and this is the phase transition that occurs. This phase 2 helium, which is at a temperature lower than 2.19 K, that shows abnormal behavior. What is that abnormal behavior? There is almost zero viscosity. You know, fluids do not show zero viscosity, but this, even being a fluid, it shows zero viscosity and can be made to flow rapidly through very narrow capillary tubes. It has been done. It is done in laboratory, okay, in cryogenic labs. And abnormally high thermal conductivity. The thermal conductivity of liquid helium 2 at these low temperatures is even greater than copper under normal circumstances. Okay, so they show such high thermal conductivity. And these novel properties can be explained using quantum statistics of a two fluid model. Again, only qualitative discussion is possible. I cannot give you any quantitative or mathematical description here. You just have to know the fact qualitatively that a two-phase liquid model, a two-fluid model is used to statistically explain these behavior. The two-fluid model contains this helium 2 phase 2 is assumed to be a mixture of two fluids. The normal fluid has just, you know, the normal properties of a fluid, whereas the superfluid has peculiar properties like zero entropy and zero viscosity. Once again, zero entropy is something that is very it's almost it sounds impossible, because we know all the system seek higher entropy. Entropy always increases. Okay, but this is something where we see there is zero entropy, and we already discussed the case of zero viscosity. So this is the novel feature of the superfluid, that and this behavior is shown by helium 2 below temperatures of 2.19 Kelvin. Okay, and can be explained
Hello, ma'am.
only. Yes, bolo
Ma'am,
bolo.
it is said that helium can climb the like the walls of the container it is kept in. How is that possible?
It is because of the capillary action. If you have a very thin liquid, usually when we want to study some capillary phenomena, we use a very low viscosity liquid so that it can flow up the tube. It's a capillary phenomena. তোমরা আসলে এই এক্সপেরিমেন্টগুলো করোনি ল্যাবে বলে না, মানে if you study viscosity, maintaining pressure difference between the two arms, we actually see the water rises up, whereas if there are impurities in the water, it won't rise up so much. Okay, this is seen in the viscosity experiment of viscosity by using just ordinary water. So if you use a very even a lesser density liquid with lesser viscosity, like say ethanol or something like that, they will quickly climb up the capillary tube. So helium, liquid helium having zero viscosity, will easily climb up a capillary tube. This again is a novel feature because of the fact that it has zero viscosity. And this happens only at low temperatures, below 2.19 K, not under ordinary circumstances. It happens only when it behaves as a superfluid. Okay. And as I told you that at this level, I do not have scope to further explain this phenomena because it involves very complex statistical mechanics.
Ma'am,
Not
just another question. Uh,
Bolo?
Ma'am, since it is such, ma'am, what happens to the one? How? Does it contract? Like, does it have surface tension like all other liquids?
Yes, it has surface tension, but it does not behave like all other liquids. How the surface tension changes with temperature, I really can't tell you because I don't know it myself. I don't know in the sense that um, this is not something that I have studied extensively. Um, as I told you, these topics are more of intense research oriented topics and very specific topics. These are not very general topics, and so I have not gone through the very what should I say, intrinsic nuances of this topic while doing my course, since this was not my topic of research. Having said that, I can tell you at least this, that it will not, even if it has surface tension, it will not behave like the surface tension behavior, the variation of surface tension, etc., will not be like ordinary fluids that we know of, because superfluids behave in manners which are very different from ordinary fluids. Okay.
Thank you.
Yes. So